and the other one from a different code. Okay, ultimate geotechnical resistance. And that's a good terminology. So the CSA as a table, I think, from the CSA, and it's from the commentary to the National Building Code. NBC is the National Building Code of Canada 2015. That's the latest one that's still used on the engineering practice. So they called it, so we calculated ultimate geotechnical resistance, Q ultimate. They multiply it by factor alpha, and they call that factor ultimate geotechnical resistance. Focus on the name. For the H2, they call that factored bearing resistance, which is fine. So it is a nominal bearing resistance multiplied by a factor. And this factor, instead of phi, it's phi subscript b. And b just refer to bearing because there's different factors for the tau or the sliding, which is something good in the H2. You don't have that in the NBCC or the CSA. It just tells you phi, and you know phi for bearing capacity, so it's shallow foundation. So it's 0.5 over here, by the way. And for the beta, it's different. So if you are in clay, you use 0.5. If you are sand, use CPT. And using CPT, use 0.5. If you're in sand using SPT, use 0.45, a bit less. If semi-empirical equation like Marhove, use 0.45. If footing on rocks, use 0.45. If you have a plate load test, that's the most expressible, or the most representative, the most representative test to determine the bearing capacity. It's a field test, so you can go higher with the resistance factor. Use 0.55. CSA doesn't have that. It's always 0.5, which is in line with that. If you have a look for the sliding, if it's based on friction like sand, it does differentiate between precast and Kent steam place in the H2. So between 0.9 and 0.8 here, it's 0.8. Based on cohesion/adhesion, which is a clay thing, it's 0.6 over here, but here it's a bit higher, so it's 0.85. And that's why I'm telling you, you will find difference between these factors in each code. So if you are using CSA, you are here, you are using, so you know the structural team are using the Canadian Highway Bridge Design Code, so you need to go and use that, or the National Building Code of Canada, so you know you need to go and use that table. If you are designing a table in the USA, if you are designing something in the USA, which is very common, we usually work a lot with our USA colleagues, just make sure you are using the H2 factors. What about the resistance factor for the serviceability limit state? Oh, so that's very critical and that's very important. For the serviceability limit state, whatever the stress you calculate that limits the settlement to tolerable limit, which again, our next module, but that stress is what we call serviceability limit state. You report that as it is, following the CSA, following the Canadian Foundation Engineering Manual and the H2. By the way, that will be different than the CSA. So CSA will tell you no, whatever you calculate for the serviceability limit state, please decrease that a little bit by a different factor. So over here, the SLS equal 1. And that's key difference between the H2 and the CSA S619. And that's a good start, a good point to go deeper in the Canadian Highway Bridge Design Code. So our factor geotechnical resistance, or our geotechnical resistance factor phi, is a function of two things: consequence factor and something we call degree of sight and the prediction model understanding. What does that mean? So consequence classification, as you can see, you have a table that shows like high consequence psi equal 0.9, typical, which is usually 1, and low 1.15. So high consequence. By the way, let's agree that up to here, we calculated our factored ultimate geotechnical resistance, okay? Now we'll show you, based on the Canadian Highway Bridge Design Code, that phi might be different than what we see here. We have 0.5 only for a National Building Code for buildings. For H2, we have some different values.